Our fourth video in Chapter 8 is on enthalpy of physical and chemical change. A physical change is a process that is a change in state of matter, like going from a solid to a liquid or a liquid to a vapor. These changes in state are accompanied by a change in enthalpy. Anytime you go from a less energetic state to a more energetic state, that requires the input of energy, and it will be endothermic. Anytime you go from a more energetic state to a less energetic state, that releases energy, and it will be an exothermic process. Now, the states of matter are characterized by their energy levels. The solid of any type of material has the least amount of energy, and this is a reflection of solid compounds. Their particles are not allowed to move past one another, and that's because they don't have a lot of energy. However, transforming a solid to a liquid is the process of giving each molecule a little bit more energy so that they're allowed to slide past one another and behave as a liquid. And then converting between a liquid to a vapor is giving the molecules more energy until they're in that vapor phase and have a lot more freedom of motion. Now, solids are the lowest energy types of compounds, liquids are in the middle, and vapors have the most energy. And so any time on this chart where we're going from a less energetic state of matter to a more energetic state of matter, that is going to be an endothermic process. And each of these changes of state have their own name for the amount of energy that's required. For instance, going from a solid to a liquid requires the input of energy that's equal to the delta H of fusion for that compound, where fusion implies the process of going from a solid to a liquid. For water, going from a solid to a liquid has a delta H of fusion of positive 6.01 kilojoules per mole. Remember, it's an endothermic process, and that is reflected by the positive sign for delta H. Going from a liquid to a vapor is also going from a less energetic state to a more energetic state. This is called the delta H of vaporization. And again, particularly for water, the delta H of vaporization going from a liquid to gas is equal to 40.7 kilojoules per mole. There is also the process of going directly from a solid to vapor, which is called sublimation. The delta H of sublimation for water, going from a solid directly to a vapor, is equal to the sum of the delta H's of fusion and vaporization. And therefore, we would get 6.01 plus 40.7 kilojoules per mole to get our delta H of sublimation going from a solid to a vapor of water of 46.8 kilojoules per mole. Now, all of these processes going up are endothermic, and therefore all of the processes going down from a more energetic state to a less energetic state are going to be exothermic. And that's because the energy that was associated with the higher energy level molecules is released as heat. Now, going from, let's start with a vapor back to a liquid, that is going to release the same amount of heat as the delta H of vaporization. However, it's going to be exothermic, and therefore the delta H of this process is negative. Going from a gas to a liquid has a negative delta H that is the same magnitude but the opposite sign of the delta H of vaporization. Going from a liquid to a solid would be the opposite of the delta H of fusion, and therefore same magnitude, 6.01, but the opposite sign, negative 6.01 kilojoules per mole for this process. And finally, going from a vapor to a solid has the opposite sign of the delta H of sublimation. So we have the value 46.8, but the opposite sign of that, So negative 46.8 kilojoules per mole, where that negative represents the exothermic process and the positive represented the endothermic process. So you will need to know the words for delta H, vaporization, sublimation, and fusion, that imply which changes of state of matter, solid to liquid, liquid to vapor, etc. And you will need to know that going from a more energetic state to a less energetic state is exothermic, and going from a less energetic state to a more energetic state is endothermic. And then use your values of delta H of fusion, vaporization, or sublimation accordingly. So let's do some practice. We have what is the change in enthalpy when 195.5 grams of benzene with a molar mass of 78.12 grams per mole is converted from a gas to a liquid. The delta H of vaporization of benzene is positive 33.9 kilojoules per mole. This delta H of vaporization means going from a liquid to a gas. And this is a lower energy level to a higher energy level, as shown by the positive value of delta H of vaporization. However, in this problem, we are going from a gas to a liquid. Going from a gas to a liquid is going from a higher energy level to a lower energy level. We're still looking at the same two states of matter, so we're still working with the delta H of vaporization. However, we'll have an exothermic process. Therefore, we'll have the opposite sign of the delta H of vaporization. We'll have negative 33.9 kilojoules per mole for this process, because we have the exothermic and we were given the endothermic. Okay, so we're going to use this similar to how we use the delta H's for a reaction. We are given our number of grams of benzene, and the delta H is in kilojoules per mole, so we need to convert from grams to moles as our first step. We have 195.5 grams of benzene. We're given that the molar mass is 78.12 grams per mole. And then we're given our delta H of vaporization in kilojoules per mole. We switch the sign, but we'll still put that 1 mole on the bottom, and then we'll say our negative 33.9 kilojoules on top. Now look at what happened. Our grams canceled out, our moles canceled out. We have our kilojoules, which would go hand in hand with the units for enthalpy, and therefore our delta H for this process is going to be 195.5 times negative 33.9 divided by 78.12, which will give us negative 84.84 kilojoules for this process. Now this video is also called enthalpy of chemical change, which is what we did when we were learning about thermochemical equations, but let's just do another problem as practice. What is the change in enthalpy when 800 grams of carbon reacts with excess oxygen according to the following chemical equation? Solid carbon plus O2 gas gives us carbon dioxide gas. We're given the standard change in enthalpy for this reaction of plus 33.9 kilojoules per mole. Oops, this was the value I carried over from the last thing. Looking at my notes here, it should be negative 393.5 kilojoules per mole. Okay, so we're given a chemical equation, and we're given a value of the standard change in enthalpy, negative 393.5 kilojoules per mole. Now remember, the not sign, the degree sign, implies standard state, 1 atmosphere pressure, and then 25 degrees Celsius. And all of our reactants and products should be in their state of matter under these conditions. Solid carbon is good, oxygen gas is good, carbon dioxide gas is good. And remember, what the change in enthalpy means is it is the change in enthalpy for the reaction exactly as written, meaning 1 mole of carbon reacting with 1 mole of O2 to give 1 mole of CO2. However, we're given an initial amount of carbon that's not equal to 1 mole, and so we have to see how what the change in enthalpy will be when this much carbon reacts, because enthalpy is an extensive property. It depends on the amount of material present. We're given excess O2, which means we don't have to worry about it. So we're going to set up our problem by converting our 800 grams of carbon, which is just C, into moles. The molar mass of carbon is 12.01 grams per 1 mole. And then the delta H of this process tells us that for every 1 mole of carbon that reacts, because the coefficient of carbon in the balanced chemical equation is just 1, for every 1 mole of carbon that reacts, there is a release of 393.5 kilojoules. And so that would be negative to imply that exothermic process. Now, to solve for this, we'll multiply 800 by negative 393.5 and divide by 12.01. The value here would be negative 2.62 times 10 to the 4th kilojoules. So when we react those 800 grams of carbon with excess oxygen, we will release 2.62 times 10 to the 4th kilojoules of enthalpy.